We're going to be doing two-dimensional motion for the next couple of days. And there's lots of application. We're going to be looking at two very straightforward applications. The first is projectiles. And the second will be vector addition. I'm going to focus on projectiles first. It is just an extension of kinematics, and it's not particularly hard. Not like what we've been doing the last weeks where there's lots of minutia. Projectiles is just more kinematics. So I want to give you some definitions here so that you have kind of an understanding of what the whole topic of a projectile is, but it is not adding anything new, just a different way to organize yourself, okay? A projectile is an object that moves in two dimensions, but experiences an acceleration in only one. A projectile is an object that moves in two dimensions, but experiences an acceleration in only one. All right. Before I go into this, I don't know how theoretical you guys want to get. I think some of you kind of like a topic of theory. I think some of you, it's first period in the morning and you prefer just to tell me what I need to know so I can wake up and do my real classes. So let me just argue that I'm not a stickler for theoretical observation, but I think there's something to be said about being considerate of what a theoretical observation is. If you're standing on top of a building, like so, and we're talking about two-dimensional motion, we, as a group, have to agree on the directions that we're going to use for comparing, like, where something goes. I know it kind of sounds silly, but we talked about this 3 weeks ago. If I want to describe for you where something is, don't we first have to agree on a place to measure that from? So, we talked about, in the classroom, if I wanted to find where you're sitting in the classroom and I want to tell somebody who's not in here where you are, well, let's define something that we can all agree upon and then take our measurements from there. Like we could say the door is where I'm taking my measurements from, and I'm going to say this way is the x direction and that way is the y direction. So you can move 5 paces in the x direction and then 10 paces in the y direction. Right? That would help you get to where this person is. But we've established already from the beginning what direction is x, what direction is y, and where the origin is. Does that all make sense? This establishment is an arbitrary decision. We can have a problem where we have, a guy standing on a building and we could decide to make the x and y direction any direction we want. But there are probably some advantages to choosing directions that have more meaning. For example, we know that if I drop a ball from this building, it's going to be pulled downwards this way. Well, if I know it's going to be pulled downwards that way, I might want to set my directions so that one of the directions lines up with the direction the ball's going. That makes my dropping of the ball a one-dimensional problem instead of what it is right now, a two-dimensional problem. Right? If I leave my coordinate system like this and I say this is y and this is x, then my object's moving in 2 dimensions, and that's going to be more complicated for me to deal with. We can pick what direction is x and we can pick what direction is y as long as x and y are at a right angle to each other. Does that make sense? So we generally try to have kind of a moment in every problem where we establish direction. Now, for the first test, it was one-dimensional motion, so we drew an arrow and said this was the direction we were calling positive. For the rest of the year, a lot of our motion is two-dimensional. So you should start your problem by identifying a positive x direction and a positive y direction. So in this problem, I'm going to be throwing something. It's a projectile. So I'm going to make the up direction the positive x direction. I'm sorry, the up direction, the positive y direction. And the right direction, the positive x direction. This establishes for you and for me a consistent set of coordinates. And I have other decisions I can make, like I can make the ground 0 if I want, or I can make the top of the building 0 if I want. Choosing an origin is also necessary, and you should choose an origin. Where are we going to make our measurements relative from? Now, projectiles, like the thing said, is motion in 2 dimensions with an acceleration in 1. So dropping the ball would be 1-dimensional motion, but throwing the ball would introduce 2-dimensional motion. This is a projectile. This object is going to be traveling both to the right and probably downwards. It's experiencing an acceleration, but the acceleration is just downwards. There's an acceleration due to gravity that is pulling the ball downwards. So we can count on. In fact, it probably all realize at this point this is going to be 10 meters per second squared. But the object is also moving to the right with whatever the initial velocity was that the guy gave the ball. With projectiles, the thing to understand is that we have 2 dimensions of motion, and they're kind of connected together and kind of not. The horizontal direction doesn't change. The horizontal speeds don't change. There's no acceleration in the horizontal direction. Because there's no acceleration, horizontal velocities are a constant. But vertical velocities accelerate. So, right now at time 0, the ball just leaves the hand of the guy who threw it. It has 1 velocity and it's horizontal. In fact, I'm going to put a little X next to it to say that's the horizontal velocity. It's in the X direction. The initial Y velocity, Vy naught, 2 subscripts. One for me to say that it's in the Y direction, one to say that it's the starting velocity. It's 0. I threw the ball sideways. Now, one of these is going to change, and one of them isn't. Clearly, the vertical one is the one that's going to change because gravity pulls it downwards. So after a moment, I think we can all agree the ball's probably going to be over here someplace. It's still moving sideways. It still has Vx. Vx hasn't changed. So if I throw it at 5 meters per second sideways, it's still traveling 5 meters per second sideways. But over the last few moments, it has acquired a bit of a downwards velocity because it's accelerating downwards. So one component of its velocity is changing, and another component of its velocity is staying the same. This word I'm going to use is going to be used all year long. You need to become acquainted with it. Velocity is a vector. We describe velocity by its components. This vector is in 2 dimensions. So a component is the part of the object's velocity in a particular direction. That's what a component is. It's the part of an object's velocity in a particular direction. So the components of the ball's velocity are the x components and the y components. The x components are the horizontal components of the ball's velocity. The y components are the vertical portions of the ball's velocity. Now, you guys are sharp people. The ball only has 1 velocity. It's traveling in that direction at that moment. Right? It has 1 velocity. We're talking about the parts of the velocity in 2 different dimensions. Do you see why trig is going to become a part of this soon? We're going to have to be able to use trig to figure out how much of something's motion is in 1 dimension compared to how much it's in another dimension. That's where the trig comes in. But I'll be using the words components for the rest of the day, so be prepared for that. After another few moments, Ball's here. Its horizontal velocity hasn't changed, still the same, but it's still accelerating downwards, so its vertical velocity keeps getting bigger. I don't think it's a big stretch, but the ball is going to travel along some curved path like that. But what's happening is that its horizontal velocity is not experiencing an acceleration, but its vertical velocity is. Eventually, it's going to strike the ground some distance away from where it was thrown. We call that horizontal distance the range of a projectile. Now, I think this part will be pretty obvious, but I like to kind of be thorough. We've been talking about motion for a couple of weeks now. When I encounter a projectile problem, one of the first things I recognize is that I can treat the vertical motion separate from the horizontal motion. The vertical motion is experiencing an acceleration. So it's going to have the 5 motion variables associated with accelerated motion. I'm going to change them a little bit because I want to differentiate them from the horizontal. So I'm going to say delta y to indicate that we're talking about a vertical displacement. I'm going to say Vy initial, talk about the initial y velocity. And Vy to represent some final y velocity. Acceleration, which is going to be the acceleration due to gravity. And time. All the things we would expect from accelerated motion. But the horizontal part, it has no acceleration. It still has a displacement, a horizontal displacement, which I just told you we're going to call the range. Because there's no acceleration, the horizontal velocity never changes. It's a constant. But there's still time. There's still how long the object moves. The thing that you need to put in your notes and make this the biggest, most important thing of the day is that the object falls for the same amount of time as it travels sideways. These problems are connected. This is a connected problem. A projectile problem is connected together by time. In all projectile problems, how long the object falls is related to how far the object moves sideways. This is a projectile problem. So I want to talk about what this means in practice. Let's go back to our little simple question. In practice, somebody standing 10 meters above the ground throws the ball 5 meters per second. Like to figure out where it hits the ground. So I'm asking for the range. This is a very basic, very standard projectile motion question. Okay? What I would like you guys to do is follow a rubric for me. That rubric begins by identifying what direction you're calling positive. So in every problem, identify your directions for positive. You have to do it in 2 dimensions now. Then, I want you to clearly and obviously create a chart so you can lay out all the data you're going to be given. This one is simple. They will become more complicated. I'm going to have a vertical side and a horizontal side. The vertical side and horizontal side will be the same every time. Vertical side will have my 5 motion variables. And my horizontal side will only have 3. And I'm always going to be looking to see if I can figure out the time. This is kind of the rubric I'd like you to use for the time being. When you're proficient, do it however you want. But for the time being, this should help you lay out your information. As with any other motion problem, you need to be given 3 pieces on this side to figure out time, or 2 pieces on this side to figure out time. Because although there are 5 motion equations on this side, for something that has constant velocity, there's just one. Right? Distance equals rate times time. So like all the other problems we've done like this, I'm going to try and discern as much information from the problem as I can. The building is 10 meters tall, so the object's going to fall 10 meters. It's being pulled down by gravity. Now here's where it starts getting a little bit more complicated. I was giving a velocity, 5 meters per second. Can you figure out where this goes in this chart? Is it an up and down velocity or a sideways velocity? So I'm probably going to put that over here in the sideways velocity. You'll make these mistakes. This is why I'm trying to kind of talk it out, because it seems obvious to me now, but just wait. There's others too, like if I throw it perfectly sideways, that probably means the initial y velocity is 0. It's not moving up or down the moment it's thrown. So that'd make this 0. Now, like every other one of these problems, I identified direction. The ball falls downwards and experiences an acceleration downwards. So I'm going to make those 2 negative. Now, we have to pause here. I think you can probably see what we're going to do from here. I need the time. So I need to either have 2 pieces of information given on this side or 3 pieces on this side. I see 3 pieces of information. Do you? So I'm going to do the stuff that's on the left side to come up with the time. I'm going to say, okay, -10 equals 1/2 times -10 t squared plus 0 times t. I don't think I have to write out the formulas ahead of time anymore. I can start putting the numbers in. Are we advanced to that point? We passed that test. So half of 10 is 5. Divide 10 by 5, I get 2. So it looks like the time equals the square root of 2 seconds. We all good with that? I think I did the math correctly. So that means 1.4 seconds here and 1.4 seconds there. I want to find where the ball hits the ground. I'm going to go to the right side now. Range equals 5 times 1.4 seconds, or looks like 7 meters. Strikes the ground 7 meters from the edge of the building. Okay. We good on that so far? All right. When the ball reaches the ground, how fast is it moving sideways? Just before it touches the ground. Okay. Is this how fast the ball is moving? No, it's moving downwards too, right? Now, you could find out how fast it's moving downwards, couldn't you? That still wouldn't tell you how fast the ball is going, would it? Because we would only, this is the x component, and this would be the y component. You would have to figure out the total velocity. That would probably mean Pythagorean theorem, don't you think? That's the kind of stuff I'm going to need you to be able to do. Again, not a lot of new information, just combining it in a slightly different way. We're short on time, but you understand that I could do this different. Like, what if I said I wanted to hit a point that was 10 meters away? How fast would I have to throw the ball now? Now, one thing I want you to think about is the building any taller than it was before? So this is still 1.4 seconds. You understand, how long it's in the air generally has to do with the vertical part. And where it lands then will have to do with the horizontal part. You guys follow me so far? This one's pretty basic, and I call any problem where the initial y velocity is 0 a type 1 problem. Just to kind of give us an introduction. I kind of find that there are 3 different types of projectile motion problems. This is a type 1 problem because the initial y velocity is 0. It has a nice simplification in it. Whenever you can work a 0 into the problem, it makes it a little bit easier. But you probably understand in this problem. If you can handle those, you are be able to get a high B on your next quiz. There's going to be other kinds of projectiles. So how about somebody punting a football? Is this a projectile? Does it have motion in 2 dimensions with an acceleration in only 1? So suddenly, probably the angle and velocity of the football are going to play a role in this. I'm going to need to figure out how much of the velocity is in the y direction when the ball is kicked, and how much of the velocity is in the x direction when the ball is kicked. So now do you see the need for us to have trig? The ball is just going to go up and back down. That's no big deal. But where it lands probably has to do with whatever this angle is and how fast the ball was kicked. So I would call this a type 2 problem. The reason I call this a type 2 problem is it does have a simplification, something that makes doing this relatively easy. The ball lands the same height it was kicked. In a problem like this, I get to make delta y 0. Every time you introduce a 0 into the problem, you make your problem easier. So this is a type 2 problem. Of course, I'm afraid you can imagine on this problem. On an engine that there is the coup de grace, the hardest of these kinds of problems. And technically, hard's the wrong word to use here. It's just more complicated. Kick the same ball, but kick the ball on top of the building. You understand this is going to be tougher, right? Because in this problem, the delta y is not 0. It's going to land beneath where it was launched. And the initial y velocity is not 0. This one's harder, because the ball is going to travel up and back down. So it's going to be more complicated. The math is harder. It's still a projectile. Luckily for us, AP Physics 1, you might have to handle one of these. Does everybody understand? All right. I think it's best if you try one on your own. So let's see. I think I've got just a few minutes left. So let's see if you guys can do one on your own without my assistance. I want to kick a ball sideways off a building so it'll land 10 meters away from the edge of the building, not draw on the scale. The building's 25 meters high. How fast do I have to kick the ball? Let's start with something you do know about. I don't want to treat it the way you've treated it before. So this is not X and Y. This is east and north. I want to take this away from what you're used to. I want to define this point in space. Okay. Now, this point in space can be attained by going out 10 paces after turning 30 degrees. Now, you can't go that way, right? Because there's going to be tables in the way. I want to find how far in the east direction do I have to go and how far in the north direction I have to go. Everybody understand our goal today for this one. Now, there's two different ways to address this problem. And you should be aware that there's two different ways. So let's make you aware. If I want to get to this point, but I can only go east or west, like an Etch-a-Sketch. How many of you have ever played with an Etch-a-Sketch? Do they exist anymore? Right? You can only move that little dot up or over. You can try and move both dials at once, but it always works out to go the wrong way. So it's up or over. You guys understand what I'm saying? So if I can only go up and over, I could go over first if I want, and then up. That defines this triangle. Or I can go up first if I want, and then over. That defines this triangle. Neither triangle is wrong. You pick the triangle that works for you. Does everybody understand? But you have to know things in order to pick the triangle that works for you. For example, I gave the 30-degree angle. If you're going to choose the different triangle, you'll have to figure out what this angle is. You understand? Now, I'm assuming you guys know how to do that. What would that angle have to be? 60. So if you didn't know this, these are complementary angles. I will use the words complementary and supplementary a lot this year. Complementary angles add up to be 90. Supplemental add up to be 180. I'm providing you the geometry I will use in this class. If you didn't know that, please write that down. So I'm going to do this based on the angle I gave you, which is the green one. Does that make sense? So I'm going to do the green triangle. But remember, when you're doing this, you draw the triangle in. You'll pick which triangle you wish to use. Do you guys understand that? So I'm not calling this a step, but in this class, you'll have to create the triangle that will solve your problem. So you create it based on what works best for your mental state, how it works for you, how you think of or conceive of the problem. And I'm throwing this out there early because it's going to be stuff like you push down on the handle of a lawnmower, right? A lawnmower handle is at an angle. Does that make sense? You'll have to define a triangle based on that. How much of that thing that you're pushing on is pushing it into the ground? And how much of that push you're pushing is pushing it sideways? That's what we're doing when we do trig. So I've decided to use the green triangle. And once you have identified your triangle, step one of any of these problems is to identify the angle of focus. This is all made up vocabulary. It's to help you and I communicate. But you have to identify your angle of focus. Sine, cosine, and tangent is all based on a single angle in a triangle. You have to define all the sides based on that angle of focus. So I have defined this as my angle of focus. From there, label your sides based on the angle of focus. So the side across from the angle is the opposite side. The side next to your angle is the adjacent side. And the longest side is always the hypotenuse. I forever see students get this wrong, but please, there has to be a right angle. The side across from the right angle is the hypotenuse. It is the longest side. If you work out your problem and you work out that one of the other sides is longer than your hypotenuse, you've done it wrong. Does everybody understand? Because I saw you guys do it when we did our practice. Now, I chose my angle of focus. That was step one. I labeled my sides. That was step two. Now, this next step is for the people who are not good at this. You want a rock-solid way to do it? I want to show you the rock-solid way to do it. Write out all three functions: sine, cosine, tangent. Leave a space, put your equal signs, and then write them out. You should know what they are. Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Mr. So Ka Toa. Now, here's the reason you left the space. Sometimes you'll be given the angle, sometimes you'll have to find the angle. So in this case, we've been given the angle. So I'm going to write the angle in. And now I'm going to go through and write in whatever sides have been given and put them in the places where they've been given. So we've been given just a hypotenuse. Now, by doing this every time and being careful about our mathematics, what I'm hoping to build up in you guys is a method, a way for you to do this on your own. Sometimes we have to do this symbolically. So if you're doing it symbolically, what I mean by that is there won't be a 10, but there'll be like W. And won't have 30, you'll have theta. So sometimes you'll have to solve these symbolically. Do you understand what I'm saying? So you can still write it out like this to do what we're going to do symbolically if you have to. But we're working with numbers today. So ask yourself this question: do you have the angle, like was the angle given, or do you have two side lengths? Because that determines what happens next. If you're working a problem where you have the angle, then go to your calculator and look up sine, cosine, and tangent of the angle that you have and write it in. Be careful. This is the one moment in this whole process where you check your calculator to make sure it's in degrees first. In this class, all angles where you'll do sine, cosine, tangent will be in degrees. So normally I would just erase the sine, cosine, and tangent, but that's not easy for you guys. So I just do this on the other side. It's like sine of 30 is 0.5. I kind of assume you guys know that. And the the cosine of 30 is 0.866. It's the square root of 3 over 2. And I don't know the tangent of 30. Can somebody tell me it? 0.57735. All right, you were given the angle. That meant you probably only had one side, but at this moment, after you have done sine, cosine, and tangent, you should have enough information to be able to determine any missing side. For example, looks to me like the opposite side is going to be 10 times 0.5. So opposite is going to be 5. And it looks to me like the adjacent side is going to be 10 times 0.866. So 8.7. Now here's the thing. You can't make a mistake if you do this last thing. You're likely, when you're done with all of that, you will have a trig function that has two unknowns in it. This will be like this every single time. That's the trig function you use to check your work. 5 divided by 8.7 had better be 0.57735. It's how you make sure you didn't screw up. Getting trig wrong will all be your fault at this point because there's always a way to check. You could also check by doing the Pythagorean theorem. 5 squared plus 8.6 squared, add together, take the square root, it's going to be really close to 10. It's going to go over a little bit because I rounded up, but it'll be really close to 10. All right, so once you've done this process, this part, all of this, and all the labeling, that's trig. The problem goes on after that. Whatever your problem is, the problem goes on, and you have to know what it is that you just found. I just found where to walk in order to make it to this point. So although the original problem was turn 30 degrees and walk out 10 paces, I could walk out 8.6 paces north and then 5 paces east and do the same thing. Right? Remember that there was a goal in mind when doing your trig. How do we do? Okay so far? Because we're going to do it again. Because You could probably recognize that I have to do this now for a different contingency, right? What if you have two sides? What if, in fact, I told you how far to walk north and how far to walk east? So this time, let's say I told you to walk north 25 paces and east 66 paces. And I want to figure out this angle and how far I'd have to walk. I'm doing this example and the example before because these represent the two most likely types of triangles that will pop up in our work. They won't have north, south, east, and west in them most of the time, but they'll be like this, okay? Now, again, the problem still is the same. You can draw any triangle you want, but this triangle was given to me in this order. You could have gone 66 first and then 25, right? The order doesn't matter. However, if you're asked to find this specific angle, it might be best to use the order that was given. Does everybody understand? Be prepared. I will be asking you sometimes for a specific angle. Now, the process is still the same. I get an area of focus, which means, an angle of focus. This is my angle of focus. It dictates how I label all the other angles. The right angle occurs when I turn and walk the other direction. That makes this the hypotenuse, but this is the opposite side and this is the adjacent side. So, after choosing my angle of focus, I labeled my sides. Still doing the same set of steps. Then I'm going to write out sine, cosine, and tangent. And then I'm going to put in opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. But this time, instead of writing it out and then erasing, I'm going to be a little more proactive. Opposite is 66 over hypotenuse. Adjacent is 25 over hypotenuse. And tangent is opposite over adjacent. Now, I am well aware that you can find the hypotenuse without doing any of this trig. I'm intentionally showing you how to do this with trig. Does everybody understand? Now again, you ask yourself, were you given the angle or were you given two sides? We were given two sides. If you were given two sides, then you were given one of the ratios, not the angle. In this case, we were given the ratio for tangent. So compute the ratio. What is 66 divided by 25? I'll count on you guys for that, because I don't know. 2.6 what?
4.
Let's go, is it even?
Yeah.
So the rest is zeros? Good. All right. Go out 4 decimal places whenever you do this because you want the most accurate angle possible, but you'll probably be able to leave this in your calculator if you're careful. Because what you want to do now is you want to do the reverse of the lookup. When you put the angle in and hit sine or do sine of an angle, it looks up the ratio that goes to that angle. You want to do the reverse of that. We have the tangent function and its ratio, so to find the angle, I take the inverse tangent of this number. So we have the ratio this time. We want to work backwards to get the angle. Again, this represents the moment when you're doing your work when you have to make sure your calculator's in degrees. And you've just done that, so could somebody find the inverse tangent of 2.64? Now, if it were me, I would hold on to some decimal places for what we're going to do. I don't have the room to write it, but you should hold on to some decimal places. Okay? Now, I want you to go one more step. I kind of indicated that you should be able to check your work with any of these. and I stand by that. So we're going to check our work, right? First, we haven't found the hypotenuse yet. We need to find the hypotenuse. But before we do that, I want you to do what we did before. I want you to compute all of the ratios. Now that you know one ratio, what is the ratio for cosine of 69? And what is the ratio for sine of 69? So could somebody tell me the ratio of sine of 69? And can somebody tell me the ratio of cosine of 69?
0.358.
Now, again, the set of steps is the same each time. The only difference this time is that we had one ratio, so we found the angle, but I still had you compute all of the ratios. That's on purpose. One of these could be used to solve for h, and it doesn't matter which one you use. So I'm going to use the top one, which is 66 over h equals 0.933. There are 4 people in the room who can't do this because I looked at your practice test. So you 4, listen up. H has got to be bigger than 66. So some of you are doing your algebra wrong. So I want you to understand that you're making a mistake. Multiply both sides by h. That's the first step. And then divide both sides by 0.933. So h is 66 divided by 0.933. Some of you are doing that algebra wrong, and I want to fix it now. By the way, what is h? 70.739. Okay. Now you could have gotten this through the Pythagorean theorem. I'm showing you how to do this with pure trig. And remember, I told you with every one of these, you can check your work. You can check your work. 25 divided by 70.739 had better be 0.358. Has to work this way. This is how you check your work. You want to make sure it's right. We good?
Yep.
I know from our discussion yesterday that we're going to try and take this problem and break it up into a horizontal problem and a vertical problem. We're only going to be successful if we know the velocity that is horizontal and the velocity that's vertical. So your job, using the trig you just learned, is to figure out for me how fast is this object moving horizontally and how fast is this object moving vertically at the time that it's launched. You just learned how to do the trig for this. Can you assemble a triangle and, using the information given, find the initial y velocity and the x velocity? I want to see if you can apply what you've just done to this arrangement. Hear me out a little bit. This is taking a little more time than I think it adequately should. But if you've never done this before, it does take practice. You have to create a triangle here. And a lot of you picked a triangle. That was obvious. You made that your triangle? That seems very reasonable. So good start. If you're using this process that I gave you, it is laborious, meaning there's a lot of labor involved. But it's a good start if you're just learning. So I'm going to have sine 35, cosine 35, and tangent 35. I've chosen 35 as my angle of focus. I'm going to label opposite, adjacent, hypotenuse. So sine 35 is opposite over 20. Cosine 35 is adjacent over 20, and tangent 35 is opposite over adjacent. Clearly, the sine and cosine is where I want to focus. So, can somebody give me the sine of 35? And the cosine of 35?
0.8199.
Now, once we're here, it's just going to be opposite equals 20 times 0.5735, which I think is 11.5. And then adjacent, it's It's going to be 20 times 0.8191, which is like 16 point something. 4? Okay. Now, you have to put that where it goes. So 16.4 is the horizontal, and 11.5 is the vertical. Now, one of these, we have to go back to yesterday, one of these stays the same all the time, and one of them changes. Which one of these stays the same all the time? The 16.4 stays the same. That is the horizontal velocity, so it stays the same. And the vertical one is the one that's going to be acted on by gravity. Now, technically, this is meters per second. This is meters per second. And technically, you could check your answer. You could do 11.5 divided by 16.4 and see if it is tangent 35. I promise it will be. But this is just the trig part of the problem. Because now I have my vertical and horizontal. I have delta y, vy naught, vy at. I have range, vx t. And this is just part of what it takes to actually do this. I put the 16.4 here. Walked around and saw a lot of people put 20 there. And it's a very common mistake, but no, the 20 is at an angle. Part of this velocity is horizontal, part of this velocity is vertical. Vy in the vertical direction is going to be 11.5. Gravity is going to be 10 meters per second squared. Remember, this is still a problem. So now I do the stuff we talked about yesterday. I decide on a direction to call positive. I make the things that are positive, positive, and the things that are negative, negative. And I deduce, is there something else about this problem that I can use? I think there is. If I'm launching something from the ground, if it's landing on the ground, then delta y is 0. This gives me 3 pieces of information on the left side. I can use that to figure out the time and put it over there. This is complicated, I know. And for some of you, it takes some practice and it takes a little bit of a experience. Now, we're not done, right? There's still a problem to be done here. And so I want to kind of continue it. I'm just going to make that a little smaller to make it easier on me. I'm going to use delta y equals 1/2 a t squared. I don't know why I'm writing the whole thing out. I think it's because of habit. So 0 equals 1/2 times negative 10 t squared plus 11.5 times t. It's still a motion problem. I can factor out a t and set it equal to 0. And that's going to leave me with negative 5t plus 11.5 equals 0. So t is 11.5 divided by 5, which is 2.08. I don't know if that's right or not. 2.28. Sorry. No arithmetic today. That's in seconds. Almost there. So many steps. But if that's the time it takes for the thing to go up and come back down, then this is the time it takes for it to go sideways. So now I can figure out where it lands. 16.4 times 2.28. A lot of steps, isn't it? A lot of steps. And trig 2. For all of you who will have trouble with this, hear me out. I want you to do it this way because, truthfully, you need to practice the trig if you're not good at it. Some of you don't have the stamina. And I don't mean that mean. If a problem takes you too long, you give up. You lose your place in it. You get distracted. You go to TikTok. I want to label these generically, okay, for just a minute. Every one of these projectile problems will be the same in this regard with what I'm about to show you. And what I mean is, if you launch something at an angle, regardless of where it lands, there's going to be a horizontal velocity and there's going to be a vertical velocity. Every single time. Your job would be to figure out the horizontal and vertical. If you don't have the stamina, then you should recognize that every single time you're going to be doing the same thing. Right? You're going to be finding the same two sides. I want you to do the trig fresh. But you guys who don't have the stamina, consider that it's always going to look like this. Every single time, won't it? The opposite side is always the initial y velocity. The adjacent side is always the horizontal velocity. You could say that the initial y velocity is always the launch velocity times the sine of the angle, and the horizontal velocity is always the launch velocity times the cosine of the angle. This will be true. You'll get the stuff wrong later in the year if you don't learn the trig, but you'll get your projectile motion quiz right. But please, practice the trig.